Welcome everybody to the second day of this amazing meeting. We are extremely fortunate to have two great speakers again this morning. We're going to start with Karl Friston. Probably doesn't need an introduction, but he's a neuroscientist in London, and also the most cited neuroscientist, I believe, of all time. I think that's still correct. So just some amazing work that we're extremely excited about. So please, Karl, share your screen. Go for it.
It's a great pleasure to be able to talk to you. Thank you very much for inviting me. I'm going to basically tell the same story that Anil and Kevin told yesterday, but using the language of physics in the first half and neuroscience in the second half. And I should apologize for this because it's going to be my basic talk, or starting from first principles. My hope is that many of the ideas that I heard you discussing yesterday are fully licensed and endorsed by this rather elemental or basic approach as seen through the lens of a physicist. Furthermore, the reason that I or my colleagues commit to this kind of explanation is if you understand the underlying mechanics and the physics of what's going on, it allows you to simulate things. So I'm justifying some of the technical details in this talk on the basis that if you can actually write down the kinds of processes and phenomena of interest, then you're now in a position to simulate and provide proof of principle. And my hope is that at some point, the agenda, the fascinating and challenging agenda that your group is applying itself to, may succumb to this kind of modeling and proof of principle. But I think that's going to be for you to decide. So this talk's going to be breathless because I have to complete it within 45 minutes. We're going to cover the statistics of life with a special focus on Markov blankets and how they induce an interpretation of self-organization in terms of inference and a very basal kind of belief updating, namely Bayesian belief updating. And then we're going to move on to a rehearsal of exactly the same story, but from the point of view of neurobiology in terms of predictive coding and how they play out on neuronal networks. And then if we have time, I want to just speak to the core notion of selfhood and argue that that may be intimately related to agency, and then ask, well, where does agency emerge from the formulation that I will have established in the first two bits of the talk. So I'm going to start with a question posed by Schrödinger. How can events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? Clearly, I'm not going to address that question, but what I want to do is just pick out this notion of a spatial boundary and note that in order to talk about anything, a particle or a person or a priest, you have to be able to distinguish or separate or individuate that thing from everything else in virtue of it possessing a boundary. And Schrödinger would be the first to acknowledge that that boundary is in itself a statistical object. And I'm going to read that boundary as something called a Markov blanket. So for those of you who don't know what a Markov blanket is, imagine some little universe, and these are the states of the universe. And these states influence each other, and these influences are denoted by these arrows or edges. And imagine we take some states, say my states, my internal states. So the Markov blanket is effectively a set of states that constituted by the parents, the children, and the parents of the children as defined by this causal coupling. And in brief, the role that the Markov blanket plays is that it provides all the information that I would need about the universe to predict how I am going to change or evolve next. Technically, conditioned upon these states here, the blanket states here, the internal states are conditionally independent of the external states. And I'm going to make a further move here. I'm going to divide these blanket states into sensory states and active states, where the sensory states influence but are not influenced by the internal states, active states influence but are not influenced by the external states. And I'll motivate this particular partition in a moment. I use the word particular partition deliberately because in effect, we've just described a particle or something more generally with particular states that constitute or are constituted by the blanket states, namely the sensory and active states, and the internal states. And this partition universal in the sense you can see it wherever you look. So here are two of our favorite things. At the top, there's a brain, and the bottom, a single cell. We can imagine the internal states of the brain being everything I'd need to write down to identify the current state of my brain, its activity, its connectivity. The internal states of the brain will influence my autonomic system, my active states, my actuators, which in turn change the external states that then couple back to the sensory states, my sensory epithelia, that then influence my internal states. And so the cycle continues. And exactly the same partition or sparse coupling can be found, say, in a single cell with intracellular states constituting the internal states that influence, say, the actin filaments that support the cell surface, that is pushed into the external states, and the external milieu reciprocates by changing, say, cell surface receptors that change the intracellular states. And again, establishing this circular causality that I read in terms of an action perception cycle in relation to the brain. So that's the basic setup. What I want to do now is to do a very brief course in physics and then ask what would happen if we put the Markov blanket back into play. So I want to start with the basics of nearly all physics that we know, articulated here classically as a Langevin equation or a stochastic differential equation. I use the description stochastic deliberately because yesterday I noticed in the chat Dennis was asking about fluctuations, random fluctuations, a kind of itinerancy that is characteristic of biotic self-organization. And those fluctuations are central to this argument. They're denoted by omega here. And all we're doing here is just writing down a universe in which the rate of change of any states of this universe is determined by some flow, which is a function of where I am, plus these itinerant or random fluctuations. I've just sketched out two states here. So this could be an oscillation in one cell of my brain. It could be my heartbeat, or it could be me getting up in the morning, doing my emails, having lunch, watching television, and so on. At any temporal scale, the kind of systems that we are interested in show this characteristic property, that they have characteristic states which they keep on revisiting. You can describe this in terms of, in random dynamical systems, a pullback attractor. You can articulate this in terms of physics, in terms of a non-equilibrium steady state. The key thing is to be something is to have characteristic states that I return to, or at least the neighborhood of. And thought of like that, we can now read this object as the probability that you'll find me in any particular state if you sample me at any random time. And that's important. It's important because we know a lot about the maths of the relationship between the dynamics, the flow, the amplitude of the random fluctuations, and this description of the space system in terms of its characteristic states or its pullback attractor. Don't worry about the equations. I'll just pick out what we need to know. This is a very generic equation known as the master equation, in some contexts, the Schrodinger wave equation or the Fokker-Planck equation. Most simply, just a description of how this probability density changes with time as a function of the amplitude of the random fluctuations, gamma, and the flows here. But we just said it doesn't change with time because I exist. So to use Kevin's notion of persistence, I persist in time. So we know that this probability density doesn't change in time, which affords this solution here, known as the Helmholtz decomposition. May sound very arbitrary, but this is absolutely fundamental, and I repeat, underwrites most of physics that we know from classical to quantum. The key thing I want to look at, though, is that it describes what's known as a gradient flow on the log of this probability. In other words, in order to counter the random fluctuations, I have to be flowing towards my characteristic states in order to stop the probability density changing. And that's the key behavior that I want to pursue for the rest of the talk. So at this point, let's put the Markov blanket back in play and write down that gradient flow in terms of the amplitude of the random fluctuations. These things denote circular or solenoidal flows that give this kind of itinerancy and life cycles and oscillations. What the Markov blanket tells you is that it is subject to the same law, and it means that the internal states and the active states will look as if they're trying to increase the log probability of, in this instance, the sensory part of the Markov blanket. And I'm going to interpret that in terms of perception and action respectively, and just ask the question, how would I then interpret this quantity here? Well, we've just said that the states that I'm most likely to occupy are those that are characteristic of me. They are literally the states that constitute my attracting set to which I am attracted. So they are valuable for me. They have meaning for me, denoted by M here. So one could read this log probability just as value, and one could spin off reinforcement learning if you're an engineer, optimal control theory, if you're an economist, expected utility theory. If you're a free energy theorist, the negative variational free energy is just a way of writing down this value function. If I just multiply this by -1, we have a complementary perspective that people in information theory will recognize. So this is now known as this negative log probability that I'm now looking as if I'm trying to minimize, is known as self-information in information theory, or more simply, surprisal or surprise. It's just a measure of the implausibility that I would sense this given I am me. And this is the quantity that is bounded by the free energy, leading to things like the Fermat's principle, the principle of minimum redundancy, and indeed the free energy principle. This is nice because the average of this thing is known as entropy. So the expected free energy or self-information is entropy. So it'll look as if I'm trying to resist the second law by minimizing the dispersion or the entropy of my sensed states. And of course, that's the holy grail of self-organization in physics and synergetics of the kind described by Hermann Haken. And indeed, if I was a physiologist, it would just be a statement of homeostasis. And I have to exist, I just have to keep my sensed physiological states within some viable bounds that are existentially consistent and have meaning for me, because they are characteristic states that I occupy. The final interpretation, which is the one I want to pursue, is that which would be given by a statistician. A statistician would read this not as the probability of some states given me, but me as a model of how my states were generated. This is known as model evidence, also known as the marginal likelihood, having marginalized out all the external states that cause my sensations. And therefore, perception and action will look as if we have it is trying to accumulate or increase model evidence. And then we can read off things like the Bayesian brain, evidence accumulation, and indeed predictive coding. So I just want to illustrate now and try and demystify that last interpretation with a worked example, just to work towards something which I think may be which may be a useful mathematical image of a system that is sort of self-caring. And I'll motivate this in using the simulation in the following way. What we've done here is simulate a lot of little macromolecules with strong repulsion and weak electrochemical attraction. And their very existence in some metric space means that their coupling is sparse in that each molecule cannot see molecules a long way away. So because we've written down the dynamics here, we know the coupling. We can go into this synthetic soup and identify some internal states on their Markov blanket. In essence, what we're doing is we're asking the question, is there a little particle or thing living in this soup that is identifiable as something in virtue of the fact that it has a Markov blanket? And indeed, there is in this synthetic soup. Here, the internal states are coded in blue. They're surrounded by the active states, say the actin filaments, if this was a little viral or cell-like structure, that underlie the sensory or the surface states that protrude into the external states in cyan here. So now we have a simulation, an in silico little thing, living at non-equilibrium steady state that we've identified because it's got its Markov blanket. The question is, what does it mean for it to be self-evidencing in the sense that it has to, on average, increase its Bayesian model evidence, or the evidence for its models of what's causing its sensory inputs? The answer is it's subtle, simple, and I think very interesting, simply because of this conditional independence that exists between the internal states and the external states. It means for any given internal state, there must exist a probability distribution over the external states, given the sensory states or the blanket states more generally. So what that means is there's a lawful relationship, a manifold or a function relating my internal states to the probability distribution over my external states. And if I read that conditional distribution as a Bayesian belief, what that means is that these internal states, in some sense, hold or represent beliefs about the external states. And we can actually go in and just look at the nature of these beliefs. And what I've done here is articulate them in terms of something called a synchronization manifold, where all I've done is just plot some mixture of internal states along the x-axis, and the probability distribution or beliefs about the external states and the actual external states in terms of their mean on the y-axis, to show this synchronization manifold here, this lawful mapping that just has to exist because there is this Markov blanket, this separation between the thing and everything else. And in this example, what we're doing is asking the question, can we numerically demonstrate that the internal states hold Bayesian beliefs about the fluctuations and the flow of patterns in the external states? And indeed they do. Here are the estimated, or the beliefs that are held, Bayesian beliefs that are held by the internal states, and the actual external states, showing that they lie within the 90% Bayesian credible intervals. And these look very much like what you'd see in electrophysiology if you just look at fluctuations of the internal states in response to certain events in the external states when these molecules leave their little soup and they're pulled back in again here. The point I want to make with this demonstration is not only that there always exists an interpretation of self-organized or self-evidencing systems endowed with the Markov blanket in terms of building beliefs, or having a process that looks as if they are tracking the states of the world generating their sensations. But more generally, this is just a description, which I'm sure a lot of you will be very familiar with, of self-organization that can be described in terms of generalized synchrony or synchronization of chaos. Exactly the sort first noted by Huygens in terms of clocks that are suspended from the same beam or wall will ultimately come to synchronize and oscillate in tandem in a synchronous fashion. That's all that's happening here. And indeed, this little drawing by Huygens illustrates that from the perspective of the particular partition into internal active sensory and external states, where the blanket states constitute the beam that's coupling the two penduli here. So from our point of view, all we're seeing here is an inside out, to use Anil's phrase, view of a completely symmetrical synchronization of chaos or generalized synchrony between two sets of states. I've never said this before, but what I will say to you, I was just wondering whether now, if we replace the external states with something else like me, we now have a mathematical image of the synchrony between that characterizes a dyadic interaction between two people. And you can imagine this being many people or many cells, an ensemble of similar kinds of things that are constituted in their by their Markov blankets, but have some isomorphism in their form, will, in minimizing their joint free energy, necessarily show this kind of generalized synchrony and this harmony that can always be read as one particle or person holding the right kind of beliefs about another kind of person, having a mutual understanding and implicitly a mutual predictability, a shared narrative, in the sense that all of this can be described in terms of increasing the evidence for my models, my narrative, my explanation of what's causing my sensations. And of course, 99% of the time, it is you that is causing my sensations and vice versa. So that's the physics part. Just to briefly summarize that, the existence of a particle implies a partition of systemic states, the states of any given system, into internal blanket, namely sensory and active, and external states that are hidden behind the Markov blanket from the point of view of the internal states. And because active states change but are not changed by external states, they reduce, or will on average look as if they are reducing the entropy of blanket states. And effectively, this means that action, the active states, will appear to maintain the structural and functional integrity of the blanket, a very simple form or basal form of self-assembly, and one could argue a very simple form of autopoiesis. Internal states appear to infer the hidden causes of sensory states by increasing Bayesian model evidence and actively influence those causes. And in my world, we refer to that as active influence, just to highlight the crucial role of actively engaging and establishing and selecting the right kind of data that is necessary to establish this kind of shared dynamic or synchronization. I'm going to end now by rehearsing exactly the same story, but using language much more akin to what the first half of Kevin's talk and the second half of Anil's talk yesterday. So this is the perspective that a psychologist or a neurobiologist might bring to the table on exactly the same phenomena. And this usually starts with the notion of the brain as a fantastic organ, generating fantasies, or hypotheses, explanations on the inside that then are put to sensory impressions to see whether they are apt to explain what's going on. And if they match, that's fine. If they don't, then you get some kind of Bayesian belief updating. I find this very nicely demonstrated by this 16th century oil painter famed for doing still lives, that when viewed from a different direction, give you a very different impression. Oops, I got them the wrong way around. So you're meant to see the bowl of fruit first, and then after that the face. And if you do see a face now, the point being made here is that you made that face. It's something that you had on the inside in your internal states that is a good explanation for the sensory impressions on your retina or your epithelia. And then this notion you can find throughout history and philosophy. I'm not a scholar, but I find beautifully summarized by Helmholtz, for example. Objects are always imagined as being present in the field of vision, as will have to be there in order to produce the same impression on the nervous mechanism. So again, what he's saying is it has to be on the inside before you can explain that sensory impression. Almost exactly the same ideas from people like Richard Gregory, the notion of perception as hypothesis testing, ideas used to great effect by people like Geoffrey Hinton and Peter Dayan in machine learning, who indeed built a Helmholtz machine based upon the work of, or the Bayesian inference and the work of people like Richard Feynman, articulating that mathematically in terms of this minimization of free energy. So from our point of view, though, let's just come back to this notion of impressions on the nervous mechanism, or sensory impressions on our Markov blanket, the sensory part of our Markov blanket. So I've cartooned that here in terms of some sensory shadows on our sensory veil. And if this dynamics, if this Bayesian mechanics induced by a Markov blanket is true, then what that means is I will look as if I am trying to find explanations for this sensory impression. What caused this particular shadow? So what would that look like? Well, we know exactly what it would look like. It has to be written down in this form from the physics. So my internal states change in a way that look as if they are trying to minimize this free energy form of this surprisal or self-information here. And it transpires that the functional form of this can be universally interpreted as a prediction error. So what does that mean? It means my internal state, say my neural activity, is changing as a function of my current neural activity plus a prediction error. And if you were an engineer, you'd recognize these as the equations behind predictive coding or Kalman filtering, usually separated into a prediction, what I predict the world will do given its current, my expectations about its current state, and then an update that is informed by the sensory data that I sample. So what's this free energy gradient here, this prediction error? Well, imagine that I had this sensory impression here, and I had an expectation, a Bayesian belief, that it was caused by a dog. And if I had a generative model that could generate what I would see if I was correct, I can then generate the prediction and compare it to the sensation to form a prediction error, which is simply the difference. And all this fundamental gradient flow is saying, this predictive coding or Kalman filtering equation is saying, is I'm going to change my mind in the sense of changing my internal states and my neuronal states until the prediction error has been eliminated and I've minimized my free energy and the gradients have been destroyed. So is that plausible? In fact, it's very plausible. It speaks to a picture which we'll see in a second, where one can look at I think both Kevin and Anil showed sort of cartoons of this. One can look at the brain as a hierarchical generative model, generating predictions, evaluating the quality of those predictions by evaluating a prediction error, the free energy gradients, and then revising beliefs, doing Bayesian belief updating on the basis of the mismatch. Now, notice at no point will I ever know what's going on out there. All I'm doing is finding a sufficiently good explanation in terms of that which minimizes my prediction errors. In this instance, it was actually a cat. But that's nice because what it means is we forget about all the physics and just summarize the existential imperative that inherits from the physics in terms of minimizing prediction error. And there are two ways of doing that. We can either change our minds to make our predictions more like sensations, or we can act on the world to solicit some more sensations that are closer to our predictions. So we can just realize our predictions actively by changing the configuration of our body, for example, or in our internal state, if we talk about interoceptive inference and autonomic reflexes, or we can engage motor reflexes, or I can look somewhere else until I see what I expect to see, and thereby minimizing my prediction errors. I won't go through this. This is what I would take people through if they did neuroscience in terms of the hierarchical organization of this kind of scheme. The basic message behind this architecture is that, say, for example, visual input comes in, it's in receipt of top-down predictions from the visual part of the brain. It elaborates a prediction error that's then sent forward to revise my beliefs to provide better elemental descriptions. But crucially, these expectations are themselves being predicted in a hierarchical sense, with these top-down descending predictions to produce a prediction error that then drives the high-level expectations, more abstract representations, to provide an account of what's going on below. This is exactly what Kevin was talking about yesterday in terms of this layer or level of the hierarchy, looking at informing and being informed by the level below, and so on to any hierarchical depth required. The particular twist in this graphic, though, is that it incorporates action. So here there's another kind of prediction error that comes from the muscles in my eye that I could predict, and I could use a prediction error to infer where my eye was currently pointing. But there's a much simpler way that I can minimize these prediction errors. I can just change the stretch of my muscle to match the predictions of the stretch receptors. And what I'm describing here is this a classical reflex arc in motor control. If I was doing interoceptive inference, this would be an autonomic reflex, basically actively and reflexively minimizing prediction errors in relation to deeply hierarchically informed predictions that are generated by my model that I'm trying to maximize the evidence for. So that's the basic story. I just want to finish the story with saying, well, actually not quite. Before I do that, let me just illustrate the kind of active inference and the kind of sort of engagement with the world, and one way of establishing a very simple synchrony with the world that inherits from the architecture I've just shown you. What we did here is basically equip a synthetic subject with a generative model that had dynamics, autonomy, and this kind of itinerancy that was implicitly referred to yesterday, in the form of a central pattern generator, and then map this abstract dynamic to some point in extrapersonal space. And we told the synthetic subject, or part of its generative model, was that there was an invisible point that was moving around, and there was an invisible spring that was pulling her finger towards the moving point. So that means that this synthetic subject is now predicting to feel her hand being moved around and see her hand being moved around. But because she also has reflexes, then she's going to automatically fulfill the predictions of the hand movements and cause the hand to move, thereby fulfilling the visual predictions. And with this very simple kind of reflexive setup, we can simulate quite realistic biological kinds of motion, and also by simply removing the proprioceptive or the movement sensing information, we can simulate not just action, but what it would be like to observe something very similar performing the same action, but just visually without the proprioceptive input. So that kind of simulation rests upon this sort of overall architecture that we get some sensations, and that they are used to do our Bayesian belief updating by minimizing this variation free energy, or what to do next. And those predictions are then used to generate action. And this rests on the Markov blanket that I showed right at the beginning of the presentation. What I'm going to do now is make one very, very simple move and take this sparse coupling that defines this thing from everything else, make it slightly sparser in a very simple but very important way. I'm going to remove the influence of my active states on my internal states. And as soon as I do that, then from the point of view of the internal states, my active states now become vicarious causes of my sensory states, which means that there now exists an interpretation of my internal states as modeling not just the external states as causing or using a model of the external states to predict the sensory states, but the external states and the active states now become causes of my sensations. So now I have a model of the causes of my sensations that include my own actions. And it's this particular move that I'm suggesting, or from the point of view of simulating these kinds of this kind of self-organization, may be a necessary move to introduce agency, in the sense that agents will have some notion, or at least can be described as having some sense of their own agency, the consequences of their own action, because their own action is now not directly accessible. It can only be observed via the sensory consequences that therefore have to be modeled. And this takes us into a slightly different and I think richer world, where you now have the notion of a model that incorporates explicitly the consequences of the agent's action. I'm not saying at this stage there's any awareness or sentience of that agency, but just it is there, that is then used to plan into the future, to evaluate the different consequences of different actions, so that you are now implicitly introducing the notion of planning and a temporal depth into the dynamics that then provide the predictions of what I'm actually going to do next. I won't go through this in any detail, but just use it to make the point that the underlying maths is quite simple and has a teleonomy, or at least an interpretation in terms of things that people in statistics, machine learning, and economics would recognize immediately, in terms of things like risk and ambiguity, or accuracy and complexity, and intrinsic and extrinsic value, where it turns out that all of these quantities that underwrite the planning that ensues from having to have a model of the consequences of my action are well established in different kinds of literature. So, for example, the intrinsic value is just the quantity used in visual search, known as Bayesian surprise. It's also exactly the same quantity that underwrites something I mentioned earlier, which is the principle of maximum mutual information, or the minimum redundancy principle. It is effectively the thing that drives our curiosity. It's the thing that minimizes expected surprise by maximizing information gain. And I can sort of strip away various sources of uncertainty and get back to expected utility. But I really want to focus in the final slide on this epistemic affordance that falls out and is a necessary consequence of just having a model of the consequences of my actions in the future, that I repeat entail a degree of planning. And if I'm, say, planning to where am I going to look next, I'm going to look to I'm going to make the next eye movement that resolves the greatest amount of uncertainty about the states of affairs out there, because that has the greatest intrinsic value, it has the greatest intrinsic motivation, it has the greatest epistemic importance. It is salient for me. It has meaning for me in terms of what I don't know about the world beyond my sensorium. And you can write this down with particular examples and produce salience maps that do actually describe quite accurately the empirical behavior of people choosing where to look next. And indeed, you can simulate this in terms of a little agent. This particular agent had a very simple universe. She was either in a universe where all her sensory input was being caused by an upright face, a sideways face, or an inverted face. And by carefully choosing where to look next, noting that she could only sample a very small part of the visual field with her fovea, as indicated by these images here and this movie here, she can choose the best places to look to maximize this Bayesian surprise, to maximize or respond to these epistemic affordances, and resolve her uncertainty about what she is looking at, and she's indeed correctly inferring she's looking at an upright face. So all that can be much more gracefully summarized by Helmholtz as follows. Each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we've understood correctly the invariant relations of the phenomena before us, that is, their existence in definite spatial relations. And with that, it only remains for me to thank those people whose ideas I've been talking about, and of course to thank you for your attention. Thank you very much indeed.
Now it's on. Yeah. Thank you, Karl. Amazing talk as always. I was wondering, what does it look like, or what insights could we get from applying this minimization or this principle to, let's say, an intertwined relationship between two entities that would be sparsely or densely coupled, where you would have one using the other as a tool in a positive way, perhaps, or neutral way, or as a companion. I'm sure you have applied that. But what does it tell us about selfhood?
So yes, indeed, that has been applied, and it's something that I thought about. Not doing the presentation that I just done, and just jumping in exactly when you actually apply these principles to coupled systems, where those two systems can be interpreted as two people. So much of the sort of simulation work that we've done has actually been based upon bird song. So building little birds who can actually sing and hear each other, and then bringing them closer until they can hear each other, and then evaluating the emergence of this generalized synchronization of chaos or synchrony, so that they start to recognize each other and engage in the same song. It does involve some turn taking, but the basic insight from that kind of study is exactly as you'd say, that provided two birds have this kind of symmetry and isomorphism, so that you and I share a common generative model, a shared narrative, the same kind of language, then it's very easy for us to suddenly fall into this this generalized synchrony, which simply means that I can use my model of me to make predictions about you, and you likewise can use your model of you to make predictions about me, which means that now there is no model. It's our model, and we just share it by taking turns in terms of singing and speaking and listening, or in this instance, singing and listening. And you can just look at the emergence of this and ask the kinds of questions, from either a mathematical perspective or from the point of view of the temporal scheduling of the turn taking and the emergence of this. Then what you do is, just to speak to your second question, is well, what would happen if one bird was a baby bird and the other bird was a very mature bird, a teacher or a parent, who had very confident dynamics, very, very precise dynamics in terms of the skilled performance of, say, a song or a language, or articulating or communicating certain beliefs, whereas the baby had a less mature model that was imbued with much less precision and more uncertainty. And what tends to happen is that the two birds sort of converge on the same model, just as they minimize their joint free energy. Put that more simply, as they minimize their mutual prediction errors, as they become mutually more predictable of each other, they converge on the same generative model. But if the one bird is much more precise, it'll pull the less precise, the younger student bird towards it. So that you do exactly get, as you were intimating, this opportunity when you have this kind of asymmetry, when there's a certain wisdom at hand, for the wisdom, which is basically precise knowledge that works and is an apt explanation for my world, to draw to it less experienced things or people, or in this instance little birds, so that they come to share again, share the same narrative. In terms of selfhood, there is an answer which is very anecdotal, it's very commonsensical, but that may or may not resonate with your perspective. If you didn't have this dyadic and generalize this to sort of any conspecifics, and sort of the notion of cultural niche construction, for example, would be one manifestation of this kind of mechanics. If you didn't have those kinds of dyadic interactions, and there was only one thing like me in the universe, then I would not need a sense of self in the following sense that in order to do this dyadic interaction, you have to infer whose turn it is to talk or listen, because you can't talk and listen at the same time. So although you may have the same generative model, you still have to infer whose turn it is to talk. In order to do that, you have to have a model of self versus other. But you only need that when you have to take turns. So if I lived in a universe where I was the only thing like me, I probably wouldn't need a sense of self. But as soon as you put me in a universe where there are other things like me, and I now have to resolve the uncertainty or test the hypothesis, did you do that, or did I do that? Did I do that, or did Mum do that? Then I would need a sense of self in order to properly engage with and synchronize. Is that the kind of answer you were looking for?
Yeah, that's amazing. Thank you. I have more questions, but I think people around me also have. Follow. Yeah.
Hey, so a follow-up to Olaf's question. At the end of that synchrony process, is it possible then that the Markov blanket boundary would then shift so that both agents were on the inside? Is it possible for that to move or be flexible in some way?
That's an excellent question. And sorry, I should have preempted that question by saying that, as soon as you start to think about dyads and triads and then ensembles, you then have a whole collection of Markov blankets. So you sort of partition this system into lots of little Markov blankets, and they're all sparsely coupled to each other. But as soon as you do that, you've now got a sparse coupling between Markov blankets. So now you have a Markov blanket of Markov blankets, and so on ad infinitum. So this notion of Markov blanket is scale free. It's not tied to any particular level. So in answer to your question, there would be no fusing of the Markov blanket. That would, So I'm thinking about sort of, I saw Mark earlier on, so he'll be smiling, but I was thinking about sort of ego dissolution and merging of sort of ego boundaries. That won't happen mathematically, no. You have to synchronize across your Markov blankets. But if there's enough of you doing it and there is an in-group, then that in-group will now itself have a Markov blanket that will be composed of those members of your in-group that separate you from the outside. So, say the institution, this might be the receptionist or the delivery person who is public facing the outside, that the internal members of that particular institution may never actually have to directly communicate with. So everything is conditioned upon the interface. If you're a computer scientist, this is just the inputs and outputs, basically.
Cool. Hi. So great. I would love to get back to that point because I think it's exactly on the sort of heart of what we're working on. But if I could just back up for a second to apophenia, this idea of seeing patterns where none exist, or our tendency to infer patterns. There are certainly accounts of those that are more structural, less reliant on this idea of construction of a model, for example, and just the way we're physically built. And I think that extends obviously to pareidolia as well. So I was interested to see that you used faces sort of twice there, and I wonder if that might end up being the kind of limit of practical compute to sort of impose a model. And again, I think there are structural accounts for why we have pareidolia. But just sort of to follow up on that and bring us back to where you were, I wonder if you're familiar with work like Andy Meltzoff's on the like me and how early like me emerges in the psychology of very young humans.
Again, two excellent questions. So the first one, I think, is actually quite fundamental. It's probably just worth celebrating that question. So the structure of the internal, if you like, state space is seen as part of the model. So you're absolutely right that the kinds of things that I can pseudo hallucinate, see are going to be fundamentally constrained by the structure of my brain and the right through to the microcircuitry, through to sort of the visual hierarchy at a macroscopic level, and all the dynamics that are entailed. So that structure has now been optimized in relation to variational free energy in the following sense, that it is basically has been selected in the spirit of Bayesian model selection, which you can now read as a mathematical image of natural selection epigenetically, but also at a neurodevelopmental scale in terms of removing redundant parts of the model. So this kind of self-evidencing fundamentally has to address and is manifest in terms of carving out the right kinds of structures, which, as you were intimating, puts fundamental constraints on the kinds of things that I can perceive simply in virtue of having the right kind of structure. And just to link that to Anil's reference to the good regulator theorem, this is very close in spirit, although I was devastated to hear that the good regulator theorem is no longer perceived as valid, but it's exactly the same cybernetic spirit, that I have to have the right kind of structure in order to synchronize with my world. And this has to be probably learned at a much slower time scale than the synaptic plasticity that one would associate with sensory learning. The second, I'm not familiar with that work at all, no, so thank you. I am familiar with sort of the role in attachment theory and the importance of things like affiliative touch and interoceptive inference in very, very early developmental, not psychology, but sort of perinatal kind of experiences. And I would imagine that the work you're referring to has something to say about things like different attachment styles and the development of mother versus self. Am I correct, or perhaps you should just send me a link?
The fellow's name is Andy Meltzoff. I'll be glad to send it along. Thank you so much.
Is that on? Yeah. Hi, Carl. This is Kevin. Thanks very much for that talk. I have a question that may be pretty broad about the distinction in just some of the phrase you use of having a model, the system having a model, which makes it sound like it's a resource that the system has sort of somewhere in it that it can utilize, versus the idea of it being a model. It just physically instantiating a model. And it feels like there's a subtle distinction between those two things. And there might even be a kind of a continuum where simple, single-celled things just are a model of the world, but eventually they may actually have a model that is a distinct, isolatable sort of resource.
Right. You've been talking to Maxwell Ramstead, I can see.
Well,
who worries about this a lot, but that's absolutely right. So if I said anything else, then I'm very sorry. What I should have been saying is, at the level at which this presentation was posed, which is about basically single-celled organisms and the like, it is a model. It's a physical instantiation of something that can be described as a generative model. Mathematically, the generative model is just a description of those attracting states that I started off with, the characteristic states that I would that characterize this particular phenotype or this kind of thing. So you are that model. You don't possess a model in a sort of anthropomorphic sense. But you're absolutely right also. I think when it comes to self-modeling, and which I'm guessing is where you're going, when you suddenly so now we're moving well beyond my comfort zone and the kind of inference and belief updating that I was talking about. But one can imagine that if my generative model now has been obliged through a process of maximizing model evidence at any temporal scale to have the hypothesis that it is me as opposed to not me, say mum or other, or me in a different context, or me in a different emotional state. So I've now got some rather deep part of the model that now becomes a model of me, the model that in being. Then I think you would be licensed now to sort of refer to that, at least anecdotally, as having a model of the model, where I am the model. And that leads to the interesting notion that as soon as you've got a hypothesis, a potential, not percept perhaps, but perhaps concept at hand to explain all your multimodal, your interoceptive, your exteroceptive, your proprioceptive, and implicitly all those pro-social kinds of or cues that are generated pro-socially, all that evidence now can be explained in terms of, well, I am a person, or I am a body, or I am a happy body, or I'm a frightened body. Then you've got now, I think, a lot of latitude to start to address some of the questions that were being addressed yesterday morning, and in particular the kinds of questions that philosophers like, that you can now entertain. Well, what would it like to be me if I didn't actually have any sentience, or I wasn't aware of being me? What would it like to be a zombie? Because you have to have that hypothesis that I am an agent before you can entertain the null hypothesis or the alternate hypothesis that it is possible to have agency without having, or is it possible to exist, which of course it probably is, without a sense of agency. Is that what you were?
Yes, absolutely. No, that's great. Super interesting. Thanks.
Thank you, Karl. This is Adam. I have a question on this temporal scale question, how it ties into the discussion or the talk that we had yesterday from Rinpoche. So to take an example here, suppose that you've got a caterpillar turning into a butterfly, or a stem cell turning into a muscle cell, or any sort of kind of predictable biological transition in which these different life stages have very unique state spaces that have almost no correspondence to each other. Now, we say that things persist. If they persist, they self-evidence. But the idea of persistence, particularly in the Buddhist tradition, is a little tricky, because the idea is that nothing really persists. There's just this illusion. and that everything is constantly undergoing change. So you could use the caterpillar butterfly example as an extreme case, but more generally, if you've got a continuous learning process, then the generative model is never the same moment to moment. There's always some bit that's changing, or often some bit that's changing. So my question would be, in those situations, if we just suppose that there is some continuous learning, continuously changing model, which is the model that is self-evidencing? Is it the model at this moment in time? Is it the average of the model over the lifetime? Is it not really an appropriate question to ask because we have to assume that there is something that persists? How would you incorporate that into the framework?
Again, excellent question. I think there are two ways you would do this. The first would be to say that the thing in of itself encompasses multiple instances, say in terms of a sequence of metamorphoses or a species, for example. So you come back to this notion of this a pullback attractor. That I can't emphasize this enough. So we're not talking about the kind of fixed point attractors that characterize classical physics. We're talking about the attractors that are characteristic of far from equilibrium systems and usually biotic self-organization. So they have an itinerancy. They can still have very low measure, but they're very space occupying. So you can imagine sort of a particular life cycle that could indeed involve lots of metamorphic changes. It doesn't have to, you can just have a developmental one, as basically being one system where the persistence is not in the lifetime of any individual, but in the recurrences of this particular kind of form. So that will be one way of doing it. If I had to simulate this, though, I'd actually use a much simpler device, which is a little bit like a sort of local linear approximation to any given curve. So I just chunk it into lots of little linear parts, and say that for this little segment, before whilst I am a caterpillar, for example, or whilst I am at a particular growth stage in my caterpillar life, then at this particular stage, this is the characteristic states of being this particular kind of caterpillar. That's my generative model. And then once I've been able to write down those characteristic states, I could then simulate the development and the active inference and the behavior of that particular caterpillar for the period of time that it was that particular kind of caterpillar. And then I'd have to change. And then I have to write down another generative model and simulate the next stage of the caterpillar's life. And of course, in so doing, you're introducing now another hierarchical level which still has characteristic states. Going from caterpillar to butterfly, from caterpillar to butterfly, caterpillar to butterfly. But it's evolving, if you like, at a slower information rate that's governing the transitions at the lower level. So it's quite a complicated answer, but it becomes very relevant when you want to try and model or simulate these things. You're normally obliged to move to an explicit separation of temporal scales, which is where your question started, to make sense of this kind of biotic self-organization that doesn't have any unique scale. And then you might ask, well, what kind of physics or maths is pertinent for that? The answer that I would give would be the renormalization group. So put very simply, what you're looking for is the same kind of laws that are evinced at every level, but just at different spatial temporal scales as you move up the different levels. And those laws are just the kind of self-organizing organization that we were talking about, the gradient flows we were talking about.
Thank you very much.